This video will cover Chapter 3, the basics of experimental design. And again, I highly recommend that you read the whole chapter. This video is really meant to cover the important ideas as sort of an overview. So let's start off with an example. Do couples who go to baseball games have better relationships than those who don't? The Center for Marital and Family Studies at the University of Denver observed that in cities with Major League Baseball teams, the divorce rate is 23% lower than in cities without baseball teams. A spokesperson for the center said, "I don't want to say having a team lowers the divorce rate, but it might help." All right, so let's talk about the type of study this is. Is this a observational study, or is this an experiment? Well, one of the ways we can figure out or determine whether or not we're dealing with an observational study or an experiment is by thinking about whether or not there's some kind of a treatment that's being actively imposed by the researchers. In this case, the researchers are simply observing or noticing that cities with Major League Baseball teams have lower divorce rates. So this is what we would call an observational study. Now, part B is asking us about one of the variables. And there's two basic kinds of variables that we're going to be interested in this chapter. One's called the response variable and one's called the explanatory variable. So the idea here is, can one variable be used to try to affect or change the other variable? Now, we have to be really careful here because one of the places, and I almost used the word cause myself, this question of does one variable cause the other variable to change is a very important question, and it's actually a very difficult question to answer with statistics. But we're going to start off just talking about this basic kind of terminology. Now, the idea here is that the divorce rate is lower for cities with Major League baseball teams. So the variable that we're focused on here is the divorce rate, and therefore the divorce rate would be what we call the response variable. Now, the theory is that Major League Baseball teams, or having one, is related to or affects or is a variable we can use to determine the divorce rate or something like that. So in this case, the explanatory variable would be whether or not there's a Major League Baseball team. And there's only one treatment. And the treatment would be whether or not the city has a Major League Baseball team. And then part D is where let's talk about this idea of cause and effect. Well, again, we have to be careful here, and the answer is we don't know. So the question is, does a city having a team cause the city to have a lower divorce rate? And the answer here is that we really can't tell. And the reason we can't tell is because we haven't done a designed experiment here. It could be that there's some other variable that causes the lower divorce rate that is only being identified or connected with whether or not the city has a Major League Baseball team. The only way we can establish cause and effect relationships in statistics is by conducting a designed experiment where we attempt to control all the other variables that might also be causing the response variable to change. So let me be a little more specific with these definitions. So the units are the objects upon which measurements are made or observed, and if the units are people, then we refer to the units as subjects. In a designed experiment, the researcher actively imposes some treatment on the units or subjects in order to observe the responses. In an observational study, the researcher simply observes the subjects or units and records variables of interest. The researcher does not attempt to manipulate or influence the responses. So again, in this chapter, we're looking really at two types of studies. One type is a designed experiment, and the other type is what we call an observational study. And so with a designed experiment, we may be able to establish a cause and effect relationship, or find evidence. But an observational study, we really can't. We can't use an observational study to establish cause and effect. So this is one of the ideas that I'd like you to learn from the section. And the reason that we can't establish cause and effect relationships using observational studies is because of the concept of confounding variables. The fact that, and again, to confound means to confuse. So the idea here is that in an observational study, there may be other explanatory variables that are confounded or confused with the variable, the explanatory variable we're studying. And in a designed experiment, what we seek to do is to try to control those other variables and just focus on the one response variable or the one explanatory variable that we're studying in the experiment or the study. So a response variable measures an outcome of the study. It's a variable that's thought to depend in some way on the explanatory variable. And an explanatory variable, and sometimes we call explanatory variables factors, is a variable that is thought to explain or cause the observed outcomes. It's a variable that is thought to explain changes in the response variable. The possible values of the explanatory variables are called the levels. The treatment is a specific combination of levels of the explanatory variable. All right, let's take a look at another example. In a recent article entitled, "Shed These Food Myths," butter, eggs, starches aren't villains. Vitamins, milk, diet pop aren't heroes. The following research study was presented. So research done at the Harvard School of Public Health showed that regular soda drinkers may have a tendency toward the weak and brittle bones associated with osteoporosis. The researchers surveyed 2,622 women who were active athletes in college and classified them as to whether they regularly drank soft drinks or rarely drank soft drinks. The proportion of women in each group who suffered from bone fractures was determined. The findings: those who regularly drank soft drinks were twice as likely to suffer from bone fractures as those who rarely drank soft drinks. So let's look at these questions. Was this an observational study or an experiment? And again, this was another example of an observational study. And we know it's an observational study because the treatment wasn't being imposed on the subjects. The subjects were able to make a choice as to whether or not as to what they ate and drank. And again, that opens up the possibility for confounding variables, muddling the results. Now, what is the population under study? Well, it's a really important question. Notice that the sample came from college athletes. And one of the things that we need to be careful of here is that our sample, that we understand where our sample came from and what population it actually represents. The other thing that we want to be paying attention to here is that this sample consisted of all women. So actually, the population being studied here is pretty narrow. We're talking about women college athletes. Now, what's the explanatory variable? How about if we put it this way, frequency of soft drink consumptions, or soft drink consumption. And what is the response variable? Well, this is going to be the proportion of women athletes, women college athletes, who suffer from osteoporosis or bone fractures, actually, bone fractures. Okay, so part E. Suppose that 2,622 selected women were obtained as follows. From a list of all women's sports events available at Harvard, 3 events were selected at random, and all alumni women athletes who participated in these 3 events were contacted for the study. What kind of sampling technique is described? Well, this is what we would call a cluster sample. And we're also asked to discuss any potential problems we see with this plan. And there are definitely some problems, I think. First of all, different types of sporting events. Well, let me put it a different way. It's possible that, or it's likely that, certain types of athletic events require certain body types. In other words, to be good at certain types, like for example, basketball players maybe are taller than normal or average. So if one of the events was a basketball game, then it's possible that we're dealing with a disproportionate number of women who are very tall. Is there a connection between being tall and bone fractures? Well, I don't really know per se, but just the fact that that's possible can taint the results of our study. So let's talk about confounding here for a minute. A confounding variable is a variable whose effect on the response variable cannot be separated from the effect of the explanatory variable on the response variable. It is a variable that offers an alternative explanation for the results of the study. An observational study is one in which subjects are simply observed and various variables are measured. Observational studies are performed for 2 main reasons. 1, to learn characteristics of a large population, and 2, to assess if there's an association between 2 or more variables. And notice we use the word association instead of the more specific kind of term. Does one variable cause the other variable to change? Again, we're studying we're talking about observational studies at the moment. So in the case when a relationship between an explanatory variable and a response variable is the goal, there are 2 primary types of observational studies. One's called retrospective. That's when we look at a study of past events. And the other is called prospective, where we look at a study of ongoing or future events. So let's take a look at another example. A report in the December 16, 1996 issue of Circulation reports on a study that finds that those who are subject to depression are 4 times more likely to have a heart attack than those who are not depressed. The study involved 1,551 people in the Baltimore area who took part in a study in 1980. In the study, interviewers asked questions like, in your lifetime, have you ever had 2 weeks or more in which you lost all interest and pleasure in things you usually cared about and enjoyed? They were also asked questions about unusual changes in their appetite and in their sleep. Based on this information, subjects were classified according to their depression status, and their heart attack status was recorded. Of the 444 who were classified as having been depressed, 27, or 6.1%, had a heart attack in the 13 years since the 1980 study. Well, while of the 1,107 who had not suffered from depression, only 37, or about 3.3%, had a heart attack. The fourfold advantage mentioned earlier was obtained by controlling for other known risk factors for heart attacks, such as age, sex, marital status, and high blood pressure. So is this study observational or experimental? This again is another example of an observational study. Now, the response variable here is the proportion of heart attacks and the explanatory variable here is depression status. Now, when in Chapter 2, we discussed the difference between a statistic and a parameter. And the parameter is a value that's obtained by sampling the entire population, and the statistics actually comes from a sample. So since this percentage comes from a sample, it would be a statistic. The last sentence refers to controlling for other known risk factors for heart attacks, such as age, marital status, sex, marital status, and high blood pressure. These types of variables are called confounding variables. All right, here's a let's do it. Southpaws face more than their share of woe living in a world that is biased to the right. Now there's a new story. Scientists say that they have found that left-handers die 9 years sooner than right-handers. It's very scary, said Stanley Corinne, a right-handed psychologist at the University of British Columbia in Vancouver. Corinne and fellow researchers examined randomly selected death records of 987 people in Southern California. The researchers said right-handers, about 94% of the group, died at an average age of 75, and the left-handers died at an average age of 66. Corinne said that the size of the group was statistically valid. He suspects left-handed people die sooner because of the way the world is built. To accommodate right-handers, the researchers found that left-handers were 6 times more likely to die from an accident and 4 times more likely to die while driving a vehicle. Alan Sherman, a professor of psychology at St. Lawrence University in Campton, New York, and an expert on handedness, said the finding is hard to believe, but the work might merit more analysis. We're talking about a 9-year difference, Searleman said. So what type of study was conducted? Well, again, this is an observational study. And the treatment here would be what is being referred to as handedness. And, one way to think about this is the researchers aren't actually imposing this handedness concept, whether somebody's a right-handed or left-handed, as a treatment, but they're simply observing the difference between these two groups. How many left-handers were included in the study? Well, let's go back and take a look. Let's see. Oh, right-handers are about 94% of the group. So that means 6% of the sample were left-handed. So 6% of 987 is about 59.22, or we'll call it 60. So about 60 left-handers in the group. So, suppose that there may have been a disproportionate number of men who are known to die earlier than women on average in the left-handers group. In this case, gender would be an example of, again, another example of a confounding variable. Another issue is that years ago, parents would try to force a child to be right-handed. It may be that some of the right-handers in the study would have actually been left-handers. And I think this is a really important thing as well. So describe a better study to compare survival rates for left-handers versus right-handers. Well, ultimately, I think what we would want to do, a better study, well, I think the best study, if we're interested in studying whether or not handedness causes people to die earlier, then what we really need to do is to apply that as a treatment. And so one way to do that would be to select a group of, maybe a group of parents that are willing to participate, or somehow randomly select a large group of children, very young children perhaps, and force and randomly assign them to groups, lefties and righties, say. So one group is going to be the left-handed writers, the other group is going to be the right-handed writers, and actually impose that as a treatment at a young age, and then follow those subjects throughout their life and see if we still end up with a difference in death rates, or in the average age when the subjects died. Here's a note. Corinne's 1992 book, The Left-Hander Syndrome, presented the results of the study and argued that for a variety of reasons ranging from less immunity to disease to a higher accident rate, lefties didn't live as long as righties. However, other research has failed to substantiate Corinne's claim, finding either a much smaller difference in life expectancy or no difference at all. Corinne has also conceded that the 9-year gap may be a little off. So if you're a left-hander, don't get too stressed out. I think that this particular study is not very credible. And mainly it's not very credible on a couple of different levels. One is because there are so few left-handers in the study. Number two, I think there are a lot of confounding variables here. And one of the biggest one is the fact that, in this age group, it's very likely that the parents were actually forcing their children to be right-handers instead of left-handers. So I think that there are probably a lot of people in the right-hand group that would have naturally been left-handers. So let's get focused on the limitations or disadvantages of observational studies. In observational studies, the researcher can only observe and not control the explanatory variables. The researchers cannot adjust for confounding variables that no one has considered, and a causal relationship cannot be established. So, why experiment? Well, and again, we're talking now about experiments and not observational studies. To establish a link between the explanatory variable and the response variable, we would like to hold everything constant except the explanatory variable that we're studying. We would change the levels of the explanatory variable to see what happens to the response variable as a result. Although we can rarely achieve this ideal situation, we can sometimes come pretty close to it with an experiment rather than an observational study. So here's some terminology of experiments. The objects on which the experiment is performed and responses are measured are called experimental units, or subjects if they're human beings. The outcome variables are the response variables. The variables that the experimenter has control over are called the explanatory variables, or factors. A treatment is a particular combination of the levels of each of the explanatory variables. All right, more definitions. A treatment group is a group of subjects or experimental units that receive an actual treatment. And a control group is a group of subjects or experimental units that are treated identically in every way except they do not receive an actual treatment. In some experiments, the control group receives a standard or existing treatment that the new treatment will be compared to. A special kind of control group is one that receives placebo treatment. Well, let's talk about this placebo idea a little bit. The placebo effect is a phenomenon in which receiving medical attention, even administration of an inert drug, improves the condition of the subjects. Experimental bias is the distortion that can arise on the part of the experimenter due to how the subjects are assigned to the groups, which variables are measured and how they are measured, and how the results are interpreted. The bias is generally in the direction of the researcher's theory. So, the way we avoid researcher bias is by using some kind of a random process when we design the experiment and allocate the subjects or the units to the treatment groups. Now, a double-blind experiment is one in which neither the subjects nor those working with the subjects knows who's receiving which treatment. And a single-blind experiment is one in which only the subjects are ignorant of the treatment they receive. An experiment would also be single-blinded if the subjects did not know the treatments, but the researchers working on the subjects did not. Or I'm not sure I said that right, but it could be single-blinded either if the researchers did not know who was receiving the treatment, or if the subjects knew and the researchers did not know. All right, let's do it. Chromium supplementation doesn't live up to its muscle-building, fat-shedding image, at least in normal doses in ordinary people, as study indicates. In contrary to many muscle builders' beliefs, the supplement may not make them stronger even if they use it in far larger doses, says one researcher. The finding is disputed by other researchers. Researcher Mark A. Rogers of the University of Maryland tested this over a 12-week exercise program involving 16 previously sedentary men with an average age of 23. Half got chromium supplements at 200 micrograms per day, the upper limit of what the federal government considers a healthy level. The others got a fake substitute. All trained 3 sessions a week for 45 minutes per session on resistive exercise equipment that had the same effect as lifting weights. At the end of the training program, both groups had become stronger, but there was no statistically meaningful difference in strength gains, the study reported. This indicates that the exercise made the difference, and the chromium supplements did not help. The results indicate that the body simply cast aside the chromium it did not need without using it to build extra money or decrease fat, Rogers said. So A, the article states that some received a fake substitute. What would this be in statistical terms? So this would be called a placebo. And the idea with giving a placebo is to control or to try to eliminate the placebo effect, or to control for the placebo effect. Suppose that the hypotheses being tested are as follows. The null, no difference in strength gains between the two groups. Then the alternate would be that the chromium group has higher strength gain. Which hypothesis was supported by the study? So to answer that question, what I need to do is to go back and try to figure out, let me see, what I'm looking for is whether or not the data was significant. So in this last paragraph, what we notice is that there was no statistically meaningful difference. And I think that the way we interpret that is the data was not significant. Therefore, the null was not rejected. So, since we know since we're being told there was no statistical evidence, or the results were not statistically significant, then what we have to realize is that the null was not rejected. Therefore, the data was not rare and unusual. Under the assumption that there was no difference in strength gains. Therefore, the p-value would have had to have been larger than 5%, the level of significance. Okay, well, that's it for this lecture. So I'll see you next time.